Welcome to the course Excelling with Mathematical Modeling. We will be continuing with our discussion of the stability analysis of difference equations. So, today we start with system of linear difference equation. So, we consider a homogeneous system of the form un plus 1 equal to some alpha times un plus some beta times Vn and Vn plus 1 equal to some gamma times Un plus some delta times Vn. So, it is a homogeneous linear difference equation. I can put it in the matrix form, which can be written as Un plus 1 Vn plus 1, which is equal to alpha, beta, gamma and delta Un and Vn. So, if I want, I can write it like this, say some Wn plus 1 equal to the coefficient matrix A multiplied by Wn, where your A called the coefficient matrix and your Wn is equal to Un Vn. Now, as you can see that 0 0 is the only solution of this homogeneous system, provided this matrix, determinant of this matrix is not equal to 0. So, now for the stability, I state the theorem which says that if lambda 1 and lambda 2, two real and distinct eigenvalues of the coefficient matrix A, then your equilibrium point 0 0 will be stable if mod of lambda 1 is less than 1 and mod of lambda 2 is less than 1. It will be unstable if mod of lambda 1 is greater than 1 and mod of lambda 2 is greater than 1. And no definite conclusion if both lambda 1 and lambda 2 is equal to 1. However, if one of them is positive and one of them is negative, we get what is called a saddle. It can be either way, either this or it can be mod lambda 1 is less than 1 and mod lambda 2 is greater than. So, I repeat the theorem that if you have lambda 1 and lambda 2 are two real and distinct eigenvalues, by distinct I mean that lambda 1 is not equal to lambda 2, then 0 0, the only equilibrium point of this homogeneous system, will be stable if mod lambda 1 is less than 1 and mod lambda 2 is less than 1. It is unstable if mod lambda 1 is greater than 1 and mod lambda 2 is greater than 1, and it is saddle if one of them, the modulus of one of them is greater than 1 and the other one is less than 1. Say we consider this as case 1. In case 2, we take lambda 1 is equal to lambda 2 equal to say lambda star. So, they are real and equal. So, the eigenvalues of the coefficient matrix are real and equal. So, 0 0, the equilibrium point is stable if mod lambda star is less than 1 and unstable if mod lambda star is greater than 1. And finally, the case 3, if they are complex conjugates. So, lambda 1 is A plus IB and lambda 2 is A minus IB. So, the roots are complex, and since there will be two roots in this case, that is two eigenvalues, they must appear in complex conjugates. So, 0 0 is the equilibrium point it will be stable, focus or spiral if mod of A plus minus IB is less than 1. It is an unstable focus or spiral if mod of A plus minus IB is greater than. Now, in all these cases, if the eigenvalues becomes equal to 1, we cannot get any conclusion. Further investigations are necessary. So, this is the case for stability for a homogeneous linear system. Now, let us see what happens when it becomes non-homogeneous. That is, you have Wn plus 1 equal to some A Wn plus some constant B. Here it is in the form of matrix. So, you can assume that Wn plus 1 is equal to Un plus 1 Vn plus 1. Your A is alpha, beta, gamma and delta, and your B is some constant K1, K2. So, if I assume that my W star is the equilibrium point, then there is no change in the generation. So, W star must be equal to Wn and Wn plus 1. So, I will replace this by W star and you get W star equal to A W star plus some B. And I can write this as A W star minus W star plus B equal to null matrix. Suppose I introduce a new variable, we call this change of origin, say Zn about the equilibrium point W star. So, I will substitute this value here and let us see what we get. So, this will be Zn plus 1 plus W star equal to A times Zn plus W star plus B. So, this implies Zn plus 1 equal to A Zn plus A W star minus W star plus B. And we have already seen that this particular thing gives you the null matrix. So, Zn plus 1 equal to A times Z. So, the conclusion is that if you have a system of non-homogeneous linear difference equation, it can be converted to a homogeneous linear difference equation. And the theorem which holds, theorem for stability which holds for homogeneous linear difference equation is also true for non-homogeneous linear difference equation. So, when the problem is given in terms of homogeneous equation or non-homogeneous equation, provided they are linear, the same theorem holds good. Let me prove this with the help of an example. Say I have a system of linear homogeneous difference equation in the form xn plus 1 equal to minus xn minus 4 times yn and yn plus 1 equal to xn minus yn. So, if you have x star y star as your equilibrium solution. So, by equilibrium solution I mean that there will not be change from n to n plus 1, and hence I can replace this xn and xn plus 1 by the equilibrium solution x star and similarly with the variable y. So, I substitute it here and you get x star equal to minus x star minus 4 y star and y star equal to y star x star minus y star. So, this will give me x star plus, rather 2x star plus 4y star equal to 0, and it gives me x star minus 2y star equal to 0. So, 0, 0 is the only solution provided determinant of this coefficient matrix, which is 2, 4, 1 minus 2, that is minus 4 minus 4 is minus 8, not equal to 0. So, 0, 0 is the only solution or the unique solution of this system, and 0, 0 is the equilibrium point. Now, you check for stability, and for that I need the coefficient matrix A, which is minus 1, minus 4, 1 minus 1. So, I need the eigenvalue of this, that can be written as minus 1 minus lambda minus 4, 1 minus 1 minus lambda equal to 0. This implies lambda plus 1 whole square plus 4 equal to 0, and this will give me lambda plus 1 whole square equal to minus 4, which is 4I square, and this implies lambda plus 1 equal to plus minus 2I, and hence lambda equal to minus 1 plus minus 2I. So, the roots are complex. You take the modulus of the lambda and you get mod of minus 1 plus minus 2I, which is square root of 1 plus 4 equal to root 5, which is greater than 1. So, this implies the given system is unstable. So, what you have done here is that you have been given two difference equation. You find the equilibrium solution, which means that there is no change from n to n plus 1, and hence you substitute xn and xn plus 1 equal to x star, yn and yn plus 1 equal to y star, and you get this particular set. You simplify this and you find out this set of equation whose only solution is 0, 0, because this determinant is not equal to 0. So, 0, 0 is the unique equilibrium solution of this system of difference equation. And then you find the matrix A and find the eigenvalues, and you see that the eigenvalues are both complex, minus 1 plus minus 2I. You find the modulus, and the modulus is greater than 1, which implies that the given system is unstable. Now, let us take the second example, say non-homogeneous equation x n plus 1 equal to 0.75 x n minus y n plus 1000, and y n plus 1 equal to minus 0.5 x n plus 0.25 y n plus 59. So, you do not have to convert this into homogeneous linear difference equation. We have already proved that whatever is true for linear homogeneous system is also true for linear non-homogeneous system. So, we just state that x star y star be the equilibrium solution, and since there is no change from the definition of equilibrium solution from n to n plus 1, we replace this x n plus 1 by x star and x n also by x star, and same is true for y n also. So, this will be y star equal to minus 0.5 x star plus 0.25 y star plus 1500. Now, you solve these two equations, which are quite easy to solve, and you will get your x and y star to be 2400 and 400. This is again an unique system. All you have to do is simplify this. If I do that, I will get 0.25 x star plus y star equal to 1000 and 0.5 x star plus 0.75 y star equal to 1500. And you can easily check that this determinant of this value is not equal to 0, and hence your 2400 and 400 will be the equilibrium solution, and it is unique. And then you find the coefficient matrix, which is 0.75 minus 1 minus 0.5 and 0.25. Find the eigenvalue of this, which is mod of 0.75 minus lambda minus 1 minus 0.5, 0.25 minus lambda. And in this particular case, you will get lambda 1 equal to 1.25 and lambda 2 equal to minus 0.25. Now, you see the roots are real, but opposite signs. So, what you do is, according to the previous theorem, you calculate mod lambda 1, which is greater than 1, and mod lambda 2, which is mod minus 0.25, which is 0.25, and it is less than 1. So, one of the modulus of one of the eigenvalue is greater than 1 and another one is less than 1, and the conclusion is the equilibrium point (2400 and 400) is a saddle. So far, we have been dealing with linear difference equations. Now, let us move on to the nonlinear difference equation. So, in nonlinear difference equation will be of the form some x n plus 1 equal to f of x n, but this will contain the nonlinear terms. And as usual, to find the equilibrium point, you have to consider that there is no change in the generation from n to n plus 1, and you replace this by some x star. So, for equilibria, you will have x star equal to f x star. So, I have replaced this by x star and this by x star. Now, to see that what will happen or what kind of condition we will get for stability analysis. And for stability analysis, we give a small perturbation about the equilibrium point. So, which means that you replace this x n by a small perturbation epsilon n about the equilibrium point x star. So, you substitute it here and you get epsilon n plus 1 equal to plus x star equal to f of x star plus epsilon n. And by Taylor series expansion, we will get this is equal to f x star plus epsilon n f dash x star plus higher order terms. We keep up to the first order. So, as epsilon n is small, f x star plus epsilon n f dash x star, and this is epsilon n plus 1 plus x star. Now, at the equilibrium point, x star is equal to f x star. So, these two values are equal and hence they cancels, and you are left with epsilon n plus 1 equal to some f dash x star into epsilon n. Now, this solution, it will decrease, so I name it as 1. So, 1 will decrease if mod of f dash x star is less than 1 and will increase if mod of f dash x star is greater than 1, and no definite conclusion if we get mod of f dash x star is equal to 1. So, the theorem is that the equilibrium point x star of the nonlinear equation x n plus 1 equal to x n is stable if mod of f dash x star is less than 1 and unstable if mod of f dash x star is greater than 1, and no definite conclusion if no definite conclusion if mod of f dash x star is equal to 1. If we generalize this theorem for two equations, say of the form u n plus 1 equal to some f of u n v n and v n plus 1 equal to some g of u n v n. Suppose you have two nonlinear difference equation. To get the equilibrium point, you have to solve u star equal to f of u star v star and v star equal to g of u star v star. So, just like the previous one, you replace u n plus 1 by u star, u n by u star, v n plus 1 by v star and v n by v star, because there is no change in the generation from n to n plus 1. And then you calculate the, in this case it is called the Jacobian matrix, which is A equal to the partial derivative of f del u, the partial derivative of f with respect to v del g del u and del g del v at the equilibrium point u star and v star. And once you do that, you calculate the eigenvalues A, and your u star v star is stable if both the eigenvalues, by taking its modulus, it's less than 1, and unstable if both the eigenvalues, the modulus of which is greater than 1. So, it's similar kind, just like the linear one. So, you have to just remember these as a formula or as a theorem, so that you can apply them to the problems. So, the eigenvalue of A, say it is lambda 1 and lambda 2. Now, quickly let us take an example. Say I have a set of nonlinear difference equation x n plus 1 equal to x n plus 2.5 times y n minus 0.1 x n square minus 1, and yn plus 1 equal to yn plus 5 by xn minus 1. Now, to get the equilibrium solution, as we have told that you have to replace xn by x star, xn plus 1 by x star, yn by y star, and yn plus 1 by y star. You substitute here and you get x star equal to x star plus 2.5 yn minus 0.1 x star square, sorry, this is y star minus 1, and y star equal to y star plus 5 by x star minus 1. So, from this equation you can see that 5 by x star is equal to 1, which implies x star equal to 5. You plug this value here and you get your y star as 1.4. So, you have 5 and 1.4 as your equilibrium point, and you can easily check that this equilibrium point is unique. And once you do that, then you calculate the Jacobian matrix. So, what you do is replace, say, state this as F and this as your G. So, your matrix A is going to be, you differentiate this with respect to x and you get, say, 1 minus 0.2 x. I replace it by star. With respect to y, this is 2.5, then g with respect to x minus 5 by x star square, and with respect to y, this is 1. And when you substitute the value of x star and y star here, in this particular case it is only x star, you will get this matrix to be 0, 2.5, minus 0.2 and 1. So, now you have to just find the eigenvalue of this matrix, 2.5 minus 0.2, 1 minus lambda equal to 0. And if you solve it, you will get lambda equal to 1 plus minus I by 2. If you take the modulus of this, then it is equal to 1 by 4 plus 1 by 4 square root of that, which is 1 by root 2, and this is less than 1. So, this implies that 1.4, the equilibrium point, is stable. And to be more precise, it is a stable spiral or stable focus. So, with that we come to the end of this particular lecture, where you have seen the stability analysis of a system of difference equation, whether it is a linear or whether it is a nonlinear. In my next lecture, we will be taking up some interesting discrete models and their corresponding analysis. Till then, bye bye.